Hi, I'm Sanjay Patel. In this lecture, we are going to prove a very basic properties of a ring which follows from just definition of the ring, and we'll define some say notations like what is the meaning of power of an element and what is the meaning of some integer times an element in the ring. So let us start with the first thing, properties of ring. So we are going to prove this result. If R plus dot is a ring, then prove the following. 0 into A is equal to 0. This 0 is not the integer 0, it is the 0 element of the ring. And A into minus B is equal to minus AB is equal to minus A times B for every AB belongs to R. Minus A into minus B is same as A into B for every A and B belongs to R. Minus 1, this 1 is the unity element. Result 4 and 5 is valid only when the unity element exists in the ring. So if 1 belongs to R, we can write minus 1 into A is equal to minus A. And minus 1 into minus 1 is plus 1. And remember again, 1 is unity element of the ring. So let us prove. The first thing, A into 0 is equal to 0. So I start with any A belongs to R in the ring. Any element is given, okay, and we consider A into 0. 0 is the 0 of the ring. This I can write as A into 0 plus 0 because this 0 is identity element for addition. It is called 0 element of the ring. So the next I can use the distributive law of the ring. So this can be separated like this. Okay. So what we have obtained is A into 0 is equal to A into 0 plus A into 0. This I can write as, say, A into 0 plus 0 is equal to A into 0 plus A into 0, because again 0 is the identity element for say addition. X plus 0 is equal to x. So I can replace this left hand side by this expression. And now we know R plus is a group. The set ring is a group with respect to addition operation. So cancellation law for addition holds, and therefore I can cancel this element and write 0 is equal to A into 0, because we know that if A plus B is equal to A plus C in a group, then we have B equal to C, and R is a group with respect to plus. So what is proved here is 0 is equal to A into 0. Okay, so that is A into 0 is equal to 0, and similarly you can show that 0 into A is also equal to 0. So the first result is proved. Now the second result. What is the second result? For any two elements A and B, we want to prove that A into minus B is equal to minus A into B is equal to minus A into B. Okay. So I will prove first that A into minus B is equal to minus AB. For that, we consider, say, X is equal to A into B, and I'll put Y is equal to A into minus B. Then I must prove that we must show that this Y is equal to minus X. That is, Y is a negative element of X, and for that, you should prove that X plus Y is equal to 0. So we consider X plus Y. X plus Y, that is AB plus minus A into minus B. This I can write using the distributive law as A into B plus minus B using the left distributive law. So this is equal to A into 0 because B plus minus B is 0. B and minus B are negative of each other. And A into 0 we have proved in the result 1 that it is always 0 in any ring. So what is proved is x plus y equal to 0, and that implies y is negative of x. But what is x and y? X is AB and y is A into minus B. So I can say that A into minus B is equal to minus AB. And similarly you can prove that minus A into B is nothing but the negative of A into B. So from these two results, we have all are equal. So from 1 and 2, we have A into minus B is equal to minus AB is equal to minus A into B is proved. So we have proved the second result also. Let us prove the third one. Here we want to prove that minus A into minus B is equal to plus AB for all A and B belongs to the ring. So this can be proved with the help of the second result. I start with LHS and write like this: minus A into minus B. This we can think as, say, let me call this as X. So if I call this as X, then I have X into minus B kind of thing. So that I can write as minus of A into minus B, because X, I am calling that element X. Let me call this as X, so that anything you can take as X. Suppose I call this whole minus B as an X, then minus A into X is equal to minus A times X. Okay, so I am using that result, that minus X into Y is equal to minus of XY. Okay, so this is equal to minus, and then A into minus B, again we can write using result number 2 as A minus A into B. Instead of this, let me just mention that by result number 2 because of 2. So we are using the result 2 at these two places. Okay, and minus in any ring is plus, that is negative of negative element is equal to the original element. So this gives is equal to AB, which is equal to RHS. Okay, so the result is proved. Let us go to the next one, the fourth result. In fourth result, it says if there is a unity element, if unity element 1 belongs to R exists, then we want to prove that minus 1 into A is same as minus A for every A belongs to R. Okay, so what shall we do here is we want to show that this number is the negative of A. So I will take minus 1 times A, okay, plus A. Let me add these two elements. So that I can write as, since the ring has unity, I can write this as 1 into A. Remember, this 1 is a unity element. It is not a real number 1. Okay, because 1 belongs to R. That is, R has unity. So A you can write as 1 into A. And this, by the distributive property of the ring, we can write as minus 1 plus A times A. This is by distributive law. Okay, and this I can write as 0 into a, because 1 and minus 1 are negative of each other, and 0 into a is equal to 0 by our result number 1. Okay, so what I have proved here is minus 1 into a plus a equal to 0. Okay, so if say x plus y is equal to 0, then x is a negative of y or y is a negative of x. So I can write that this element is negative of minus negative of a. Okay, so it is proved. The last result is about the element minus 1, 1. Let me call it number 5. What is to prove here is minus 1 into minus 1, okay, is equal to plus 1, where 1 is the unity element of R. So if 1 belongs to R exists, we can write down this result. For proving this, we'll be using the previous result. We know that minus 1 into a is equal to minus a for every a belongs to R. Okay, so let us put a is equal to, say, minus 1 belongs to R. Okay, if 1 belongs to R, so its negative also belongs to R. So putting a equal to minus 1 here in this result, what we'll get is minus 1 dot, putting a equal to minus 1 is equal to minus of minus 1, and that proves the result. Minus 1 into minus 1 is equal to plus 1, because negative of negative in any ring is equal to the original element. So it is proved. So hence the result is proved. So we have proved some basic properties of the ring just using the definition and the axioms. Okay. The next I would like to introduce some very useful notations and so definition in ring. So the first notation I am defining like this. Let R plus dot be any ring, okay, and I take one element A belongs to the ring R, and I am taking one positive integer n belongs to n. Then I define two things. The first thing is the meaning of n times A. Remember here n and A are different type of elements, different types of objects. In ring, when we write A dot B, here A and B both belongs to the ring R. While here in this multiplication, both elements n and A are not in R. N is an integer which need not be in the set R, because if R is set of matrices, then n does not belong to R. So n times A, we define the meaning of this as A plus A n times. So this is my definition of NA. And second thing I want to define is A raised to n is equal to A into A n times. So we are defining an integer times an element A and some power of an element A in the ring. Okay. Then with the help of this, we can show some useful result which we are just mentioning without any proof. But let us understand the meaning of these definitions. So for example, if I consider a ring, say z phi comma plus phi comma dot phi, okay, then in this ring let me take an element A is equal to say class say 2. This belongs to z phi, and I am taking say n is equal to says 4. Let us take n is equal to 4. Okay. Then the meaning of NA, that is 4 times this class 2 is class 2 plus. Here this plus is the addition modulo phi. So we should write class 2 plus class 2. How many times? 4 times. So 2 is added with itself 4 times. Okay. So this will be very useful in our discussion. So there are 2 ways you can write the value of this. You can keep on adding 2 at a time. So I take these 2 plus 2, 4, and 4 modulo 4 is 4. So I can get 4 plus 5, 2, means using the associative property or group. Then 4 plus 2, that is 6, and 6 is equal to 1 modulo 5. Okay. And 1 plus 2 is equal to 3, and 3 modulo 5 is 3. So 4 times 2 is 3. Or you can do directly, as you know, 2 plus 2 plus 2 4 times. This I can write directly. 2 plus 2 plus 2 4 times is 8, and 8 is equal to say 3 congruent modulo 5. Okay, we know that 8 is congruent to 3 modulo 5. So that's why we can write like this. And the second thing is the meaning of 2 raised to 4. Well, let me write this way. A raised to 4, that is class 2 raised to 4, means class 2 dot phi, class 2 dot phi, class 2, and 4 times. Okay. As I have shown, you can multiply any 2 elements at a time and then write the value, or let us directly multiply all the elements. 2 into 2 into 2 into 2, that is 2 raised to 4 is 16, and we have to write 16 modulo 5, which is nothing but 1. Okay, because 16 is congruent to 1 mod 5. So this is the value of the power of an element and integer times some element. And based on these definitions, we have some results which I am going to mention here. So some results which we are assuming without proof. Let R plus dot be a ring. Okay, and suppose A and B belongs to R, are any 2 elements, and M and N are natural numbers. Okay, then we have the following results. So these results are very useful. So first one is N into A plus B is equal to NA plus NB. Number 2, M plus N times A is equal to MA plus NA. Third result is N into M into A is NM into A. That means if you want to find 2 into 3 into some element of the ring, that is same as 6 times that element. Okay, and from this we can say if you put M equal to -1, well, okay, that is not the case because I am taking M and N positive integers. We can also define and extend this for negative integers also. Okay, and this is true for all integers also. So there is no harm in writing N into minus A is equal to say minus N times A. Okay, minus N times A. So this all are true even for integers, not necessarily say natural numbers. That can be proved very easily. And this other set of results is for powers, say a raised to m into a raised to n, same as that power indices rule. Then a raised to m raised to n, we can write as a raised to mn. Okay, a raised to mn. And the next thing we want to define is a into b raised to n is equal to a raised to n into b raised to n if R is commutative. If R is commutative ring. Otherwise, we cannot write this type of result. Further, one very important thing I must tell you is in a ring with unity only, we can write the following two important things. So if R plus dot has unity element, then we can write a raised to 0 is equal to 1. Otherwise not, for every a belongs to the ring R. So a raised to 0 equal to 1 is defined only when the ring has unity 1. And second thing is a raised to minus n, or let me write this way, a raised to minus n, okay, is equal to a inverse raised to n or a raised to n inverse in the ring only if a is a unit element or a has multiplicative inverse. A has multiplicative inverse in the ring. So in the ring with unity, we can write down these results. And for the second result, we need an additional condition that A is a unit element of the ring. Unit means something which has multiplicative inverse. Okay. To understand this last remark, let us take the same example of our ring. For example, in say the ring Z phi plus phi dot phi. Okay. If I take say a is equal to 3, a is equal to 3 belongs to Z phi, then the first thing says 3 raised to 0 means 1. That is the first result. That is very simple. Not only for any element, a raised to 0 is equal to 1 because unity element 1 is class 1 in Z phi exist. And second thing I want to say is say what is the meaning of class 3 raised to minus say 2, class 3 raised to minus 2. This means you can say 3 square inverse. Remember, 3 is a unit in the ring. 3 is invertible element. In fact, all elements in Z phi has multiplicative inverse that we know very well. So this is equal to say class 9 raised to minus 1. But class 9 is nothing but class 4 modulo 5 and 4 inverse in the ring Z phi with respect to multiplication. Remember, this is with respect to multiplication is 4 for the 16. So it is 4 itself. Okay. 4 inverse is 4 because 4 for the 16 and 16 is equal to 1. So 4 is the inverse of itself. So class 3 raised to minus 2 is equal to 4. So that is the meaning of a raised to minus 2 in the ring. We can compute this also in a different way. Say class 3 raised to minus 2, we can compute directly first by finding inverse and then taking the square. So 3 inverse. What is the inverse of 3 in ring? Say 3 to the 6. So inverse of 3 is 2. Okay, because class 3 into class 2 is equal to 6. 6 means 1. So inverse, multiplicative inverse of 3 is 2. And this class 2 square is 4. So we are getting the same value whether you compute using this way or using the other method. So these are the some important notations and results which you should remember. And we are going to use this at different places in the ring theory. So from the next lecture, we are going to start some important type of rings, and then we'll discuss, say, theorems based on rings. So till then, goodbye. Thank you.